new one. We're going to find the intervals on which f is increasing or decreasing. Find the local max and min values of f. Find the intervals of concavity and inflection points. And this is our function. So what we're going to do is look at the increasing, decreasing test. So if our derivative of f is positive on the interval, then f is increasing. If our derivative is negative on the interval, then f is decreasing on that interval. And then we're going to look at our local max and min. So here's our function, and we're going to take the derivative. So f prime of x equals 12x squared plus 6x minus 6. All right, let's factor out a 6. You get 2x plus x minus 1. And we can factor that further as 2x minus 1 and x plus 1. So I set this to 0, and your critical numbers are x equals 1/2 and x equals negative 1. So when we're talking about interval increasing and decreasing, what you're doing is you're looking at like this sine diagram, negative 1 to 1/2. So the intervals we want is what's happening with our graph when x is less than negative 1, what's happening to our graph when our graph is in between negative 1 and 1/2, and what's going on after that. So when x is greater than 1/2. And we're going to use this. We don't really need the 6 here. So we're going to use these intervals and determine where it's increasing and decreasing. So I'm going to set this up and go in order. So we have x minus, x is less than 1. We need x is less than negative 1, is less than 1/2, is greater than. And then we need x is greater than 1/2. So these are our intervals here. Now let's put in our values. So we're going to look at, for less than negative 1, that was going, let's just put 2x minus 1 and x plus 1. Those are where we got our values. And what we're doing is we're looking at 2x minus 1 and x plus 1. And we want to know where is it positive, where it's negative. So if I put in a value less than negative 1, so if I put negative 2 in here and a negative 2 in here. So if I plug in negative 2, this is going to be negative, this is going to be negative. So that's all I'm doing. And then your derivative for f prime of x, 2 negatives make a positive. Since this is positive, that means your function is increasing on the interval negative infinity to negative 1. So it's increasing because this is positive. And that's what this says. All right. So in between negative 1 and 1/2. So let's just plug in 0. If I plug in 0 in here, I'm going to get negative. If I plug in 0 on this one, I get positive. So negative, positive. Negative times a positive is negative. Since this is negative, that means it's decreasing on the interval negative 1 to 1/2. So decreasing. And then the last one, we want greater than 1/2, so I'm just going to plug in 1. Plug in 1 in here. If you plug in 1, this is going to be positive. Plug in 1, positive. So these are two positives. Positive times a positive is positive. So that means it's increasing on the interval 1/2 to infinity. All right. Now, what does that tell you? What it tells us is for the min and max, If it changes, so we're looking at -1. Remember, our critical values were -1 and 1/2. So from -1 here's our -1. It's going from increasing to decreasing. So it's going from positive to negative. That means it has a local maximum. So f of -1, and I already plugged it in for you. So when you plug in -1, you get 6. That means you're going to have a local max at -1. And so that means it's increasing to, let's see, we did -1, so that's increasing to decreasing, so increasing to decreasing. That's where you're getting your local max. Now, from where the other critical value is -1/2. Well, it's +1/2, sorry. So you're going from 1/2 to 1/2. That's going from decreasing to increasing, or negative to positive. So since it's going from negative to positive, that means we have a local minimum at 1/2. So f of 1/2, which happens to be -3/4, that's going to be a local minimum. So that's going from decreasing curve to increasing. That's why it's a local minimum. All right, the next thing we're going to do is talk about the concavity test. So basically what we're looking at, and we have a continuous function, but if our second derivative is positive on the interval, then that means it's concave upward. If the second derivative is negative on the interval, then the graph is concave on the interval. So I'm going to take the second derivative, and our first derivative was, let me write our first derivative, was 12x squared plus 6x minus 6. So when you take the second derivative, you're going to get 24x plus 6. Set this to, let's factor it first. So you pull out the 6, that's going to be 4x plus 1 equals 0. So that means x is -1/4, and that's what you're looking at. So, looking in this, let's read what it says. So for our f double prime of x to be positive, then that means, and looking at this number, x has to be greater than that number. When you look at it that, so if I plug in 1, this will make this positive, for this to be a positive number. For it to be negative, I have to make my x less than -1/4. So I'd have to say plug in -1. If I plugged in -1 here, that would give me a negative for this to be true. So what this means is for it to be positive, that means it's for this to be greater than -1/2, that's concave up. And for this one, that's going to be concave down. Now, all you need to know is that since it's switching from up to down, that means you could have down to up. If it said up to up, you don't have an inflection point. But because it's switching from up to down or down to up, that means you do have an inflection point. At -1/4. And then you just plug in your -1/4 into your original equation here, and that gives you the exact value. So I'll put it up here. Again, I already did this one. So your inflection point is -1/4, comma, What did I get? 21 divided by 8. Yes. 21 divided by 8. You can always just plug this in and use your calculator if you want. And that's it. Thank you. Have a nice day. Bye-bye.